Welcome to the 12th lecture of mathematical finance. So as we started last time already, we want to talk about or discuss the pricing and hedging of financial derivatives, and in particular currently the pricing and hedging of European options. Should we recall a bit our current setting? So what we consider, and this is basically what we consider throughout the rest of the courses, we consider an arbitrage-free market. So this is the model for underlying price process. So we have one risk-free asset, which models some bank account, and then de-risky assets, here described by the vector S. And this is supposed to be arbitrage free. And well, to make our life a bit easier, we assume it's a finite market. So the underlying probability space has only finitely many elements. Think of the binomial model. This is the standard assumption example. And in this case, well, it's fulfilled. Okay, now, well, this, and if you have we want now to sell and trade a financial option on this underlying market. This should be a European one, and we call this for short claim if this is, well, as usually a random variable measurable with respect to the information revealed up to the terminal time. Measurable random variable, and by our no arbitrage principles, it makes sense to agree that this is supposed to, the claim is supposed to be non-negative, because we would not exercise the claim if we would face some losses. Okay. And last time we already have seen that, well, if you have this setting, last time, last times, I've several lectures. So first, let me also recall the first fundamental theorem, asset pricing, just fundamental pricing, because I mean, this is a very basic central result we will use basically all the time. So this is arbitrage free. If and only if the set of equivalent martingale measures is non-empty. And well, what we also have seen, if psi is replicable, so we can find a trading strategy producing at the terminal time exactly the same payoff than the option psi. Then, well, the price process is of the option psi. So the price we need to pay at time t for the option psi is given by the value of a replicating trading strategy. And this is independent of the trading strategy, replicating strategy we choose. So in particular, the price process is here for replicable option psi. It's a unique process. hedging strategy. So this is our current state of our knowledge, and now we want to use at the first step, and we want to somehow understand better what how the prices can be determined by the market information. And one way to do so, which is rather useful also, like if one want to explicitly compute prices, is that one can derive this price process here. So price process of the option psi can be determined by the equivalent martingale methods. Okay, so that's the first new lemma for today. This lecture notes is lemma 4.6. Okay. So what it says, so if setting as usual, so let me state it once again, our underlying market has to be arbitrage free, because then only then it's reasonable to talk about pricing and hedging of financial options. So it's a finite arbitrage free market. And we wanted to talk about claims which are replicable, because there we had the idea of using the law of one price to determine this unique price process. Right. Now, I promised you that we can determine the price process of the option psi in terms of the equivalent martingale measures. So let us take, as usual, by Q. So Q is a equivalent martingale measure. And recall, I mean, there might be more than one. So the price process is given by the discounting factor multiplied with the conditional expectation of the discounted claim, and then conditions to the information up to time t. Okay. Particular here, this is what we know that from the previous results we already developed, we know that this price process for replicable options are unique. So this means that here the price process, given by the martingale measures, is always the same. Doesn't matter which martingale measure you take. Right, so here, just to write down what I just said, as this is useful or important to note for future. The price process is independent of the chosen equivalent martingale measure Q. So even if there, if you have a general financial market which is arbitrage free, there might be a convex set, so infinitely many martingale measures. It doesn't matter which one you pick. In order to price your replicable option, this will always give you the same result. Okay. So let's start this proof here. Okay. Right. So the first thing is right, there exists a martingale measure because the martingale is the market is arbitrage free. This was the first fundamental theory at asset pricing, as we just have recalled, and there exists a replicating trading strategy, right? Because we have a replicable claim. So, fine. Replicating strategy for phi, right? So these are given by the assumption of this little lemma. And now what we know, if we consider the discounted value process of the self-financing trading strategy, this is a martingale under Q. This was shown by our characterization of martingales, and this is actually an equivalent definition. If this holds for all self-financing trading strategies, then Q is a martingale measure. So we know the discounted value process is a martingale measure, is a martingale under Q. Well, so what can we derive from this? Well, if we look at the discounted value process at time t, well, we can use this martingale measure, martingale property under Q to represent this as the discounted terminal value and then conditioned on the filtration up to time t. And now, well, this phi was a replicating strategy. So this here is nothing else than the discounted value of the claim conditioned on FT. And this holds, of course, for all t in the ZT. Okay. Well, but now let us use the lemma we proved last time at the end, which is so this is at least part of the content. So this is lemma for 5. So if we have a replicable option psi, the price process is given by the value process of any replicating strategy. So this means I consider the price process. This is given in particular by the value process with respect to this replicating trading strategy phi. Now I can, well, introduce my discounting factors. So I multiply and divide by BT of the value process time t. Well, but now here we have, this is the discounted value process, so we can use the equality we just derived above to see, okay, we have here the discounting factor, and then we have Q right. Okay, so this is just here So this year we make another color. Okay. And that's what we wanted to prove. So this is the pricing formula which holds under any martingale measure Q, which we claimed in the lemma 4.6. Okay. So what we have seen yet now is if we have a replicable option or claim, then we basically are done. We know how to price and hedge options, right? The replicating strategy. And in the binomial model, I think next time we will see, well, this is even, I mean, we can do it explicitly. If we write down an explicit model, you can derive explicitly what the trading strategy is or the replicating strategy is and what the prices are. Of course, they depend on the underlying model. But of course, it's rather, let's say, unrealistic that every claim is replicable. Because then, I mean, what is basically use of options is because everything can be replicable, so you can always represent any options on the market by trading in the market. So if you buy an option, this just means someone is doing the trading for you. So it's actually more realistic to assume that not every option is really replicable. This brings us to the next definition. Which is the notion of complete and incomplete markets. So a market is called complete if every claim is replicable. So if we have a market where we can replicate every option, that's a complete market. And well, we have seen that the binomial model with one trading period is such a complete market. So I mean, there are examples of models which are rather nice because we can replicate every option, which makes then also the hedging and pricing of the option in such a model much easier and more tractable. And well, and then obviously an incomplete market is a market which is not complete. So market ST is called incomplete if it is not complete. Okay. Okay. So of course, there are many examples of incomplete market. And as I said, if you look at the reality, I mean, the uncertainty about the future is so big that it's rather unrealistic that you can replicate any payoff. And one example of an often incomplete market is a trinomial model. Right. So what is a trinomial model? That's you won't be surprised. So you have let's consider it in one step. So you have time 0 and time 1. As usual, you have your risk-free bond given by 1 plus R for T. And we have an interest rate R being bigger or equal, strictly bigger than -1. And you have risk-free, a risk-key asset. So you start with the non-negative price, and then S1, so the price at time 1 depends on the future outcome. So let me draw the picture, that's easier. Right, so you start with time 0, which is a non-negative real number, as I said, and then the price either goes up or it goes down, or it goes down, and then you introduce now a third option, which is somewhat in between, so a medium move. And then you have here, of course, more than so probability 1, 2, 3, and these are probability measures. You have to have that these are non-negative and are strictly positive, so that's really a trinomial model. So this is your trinomial model, and you see if you want now to trade and sort of to replicate an option, you end up with, well, 3 possible payoffs in general. And if you want then to replicate the option, if you recall what we have done in the binomial model, we have then 3 equations and 2 unknowns, because we still have only 2 positions, one in the risk-free asset and one in the risky asset. So we have 2 unknown, 3 equations, which means in general this is not solvable. So here you can see the model is arbitrage free, right? This can be ensured easily by similar condition as we have seen in the binomial model, but not complete by the argument that we have 3 equations and 2 unknowns. For suitable. So you're invited to amuse yourself to figure out how to choose the parameters to indeed get such a parameters to ensure that this market is arbitrage free but not complete anymore. So check yourself. And well, another example will be on the next exercise sheet or on Friday, where you also will find a market which is still arbitrage free but not complete anymore. Okay. Right. So what we need to understand now, since, well, there are many examples of financial models which are arbitrage free but not complete anymore, well, we need to understand what is the price of an option if the market is not complete anymore. Okay, so let's do this. Okay. So let me recall what we meant by arbitrage free. I mean, okay, let me recall some notion at least. So if you have a claimed psi, the set pi of psi is the set of all arbitrage-free prices. The idea we had was, okay, these are those prices. If we enlarge the market by the price process of this option psi, this is still an arbitrage-free market. And this might be now not unique, I mean, not set consisting of only one element. So in principle, it's a set, so there could be more arbitrage-free prices in it. And we will see for not replicable option, this is indeed a set and not a number anymore. And this means it makes sense to consider these no arbitrage bounds. So we want to understand what's the minimal price. This will be an infimum, so it will be not attended. And which is the max, so the supremum in this set. Okay. So let's start now. What is the price for not replicable option? Of course, I mean, this is also true for replicable ones, but I mean, the idea is that we actually care about the case that we are not replicable. This is the content. I mean, at least we start with the proposition 4.9 in order to understand better what is this, the set of arbitrage-free prices. Okay, so as usual, we have our finite and arbitrage-free market. And we have an option psi. So this is our claim. Then the set of arbitrage-free prices, pi of psi, is given by the set of all expectation under a martingale measure Q of the discounted claim. Q is a martingale measure, and this still is usually the discounted version of the claim. Since the market is arbitrage-free, this set is non-empty. This is not surprising if we have this equality here, or if we can prove this equality here, is that the lowest, I mean, the infimum of the arbitrage-free prices is given by the infimum of all martingale measures Q star. So all equivalent martingale measures of the expectation of the discounted claim. And then the supremum, the arbitrage-free prices. Yeah. Is given by the supremum of all martingale measures, and then the expected value of the discounted claim. What? Okay. Okay, this is what we have to prove. You see, in particular, the set of, and this might be remarkable here, the set of arbitrage-free prices is non-empty, right? Because if we have the equality here, you know there exists a set of martingale measures which is non-empty. So the left-hand side of this equality is surely non-empty. So they are, I mean, even if the claim is not replicable, there exists arbitrage-free price. Okay, so let us work through the proof. So we have, we want to show here the equality. We can give this equality a label. So let me label this as an lecture note by 4.2. Okay, right, so we want to show this equality here in 4.2. And this means we have to show two directions. The first one is that if I have an arbitrage-free price, then it's also in this set here. Oh, I mean, okay. So let's take an arbitrage-free price. So that's arbitrage-free price. This means there exists adapted heuristic process. Let's denote it by D+1, right? This is the idea of our extended market. So just that the conditions are fulfilled. So we, so this is, for one, is not important here. So this means the, at the time 0 as D+1 at time 0 is exactly peak psi. It's a non-negative process, and at the terminal time, it's equal to the obtuse psi. And this is just included in this 4.1. And this is more, we focus here, the extended market is arbitrage free. Okay. But if the extended market is arbitrage free, this means there exist equivalent martingale measures on this extended market. There's fundamental zero asset pricing. They exist. Equivalent martingale measure Q for the market. We note here that the set of martingale measures, even if they're not very precise, so the set of martingale measures, of course, depends on the underlying market, right? Because the martingale measure is a measure which turns the discounted price process into martingales. And so the set of martingale measures for the enlarged market and the original market might be different. So for the enlarged market, there might be less martingale measures than on the original market. Okay, and this means applies, and this is the definition. Martingale is if I consider the ETH price, where it's supposed to be a martingale, so it is given by the conditional expectation under this measure Q of the terminal price conditioned on the information up to time t. So for all t and I in 1 to d+1 now. Huh? Okay. But this means in particular, I mean, I can apply this equality for the d+1's asset, right? The price process. So this means the price here which is equal to d at time 0, and this is was included in this property 4.1. And now I use the martingale property under Q. And condition it on F0, martingale property. And since we have a trivial sigma algebra at F0, well, you can forget this conditioning here. Have just the expected value, and at time terminal t, this is just the discounted claim. Okay. Well, and this is exactly what we wanted to show. This means this pi of psi, which is included or can represent it as an expected value under some martingale measure. Of the discounted claim, because I mean a martingale measure on the extended market, is of course also a martingale measure on the original market. So this is in here. Okay, so this is one direction. All right, so let us go for the other one, which is this one. Okay, so what we suppose now, let's call it again d plus 1, is we have an element in this set so what does it mean? There exists martingale measure Q again in this, well, which is equivalent martingale measure, such that d plus 1 at 0 is equal to the expected value under this martingale measure Q of the discounted claim. This is just the definition of this set. Okay, so now we need to construct a price process to verify that this d S0 d plus 1 is indeed an arbitrage-free price. So for this purpose, let us define the following process. D plus 1 at time t. Right, so how do you want to define it? Well, we want that we know what the value at time as 0 and at time t should be. We want to have an adaptive process. Well, this is always ensured by taking the conditional expectation. And we want that's non-negative. Well, obviously, that's the choice. And because this is non-negative, because the claim is non-negative, and at the terminal time and at the initial time, it has exactly the properties. And now we forgot the discounting factor. Because if we discount here, sorry, I wanted to discount this to have martingales here, so we need to redo the discounting. So this is the choice I want to make, and it's a non-negative process matching the terminal conditions and the initial condition. Okay. Right, and then what do we get from this? So just to mark. So what we see first is, as I discussed verbally here, we have that our condition 4.1, which are the conditions of a arbitrage-free price process, are fulfilled. And well, this here is a martingale. So if we discount it, so the measure Q, which we picked here, is still a martingale measure. equivalent martingale measure for the extended market. And this is why I needed to introduce here the discounting process. So for the extended market, there's now D plus 1 risky assets. Okay. Right, because it's a martingale measure on the original market, so all the discounted price processes are martingales, and then I've discount the D plus 1's risky asset here as defined here. Then it's a martingale by construction. Okay. Well, and now this is our most important theorem so far. Well, the first fundamental theorem of asset pricing. This implies the extended market or the enlarged market here is arbitrage free because we have a equivalent martingale measure for it. In other words, this E plus 1 times 0 is indeed an arbitrage-free price. Okay, so it was not too hard. And now, so we have shown now the quality here of the set of arbitrage-free prices can be represented as expectation under the equivalent martingale measures. And final remark should be that we have then also the representation of the infimum and the supremum in terms of martingale measures. Okay. Okay, let me. Right. So we use now the quality here. So this is the, for 2 is just the quality of the sets we just have shown. And this means from this, we get immediately that, well, if we take the infimum over all arbitrage-free prices, psi, this is, and just to recall the definition, this is the infimum over this set, and this is obviously the infimum in the same set, just represented by martingale measures. Okay. And the supremum is the supremum of this set is equal to the supremum, of course, sorry. Right. And these are actually well-defined finite numbers. Sure. Just a remark that nothing goes wrong here. So note and well, the other set. Here, these are the 2 sets. are bounded from below by 0, well, because the claim is non-negative, so price, I mean, it should be always non-negative, and from above by what is above? Yes, we have a finite probability space, so just take the supremum of the discounted claim here, which is finite, as we have a finite space. So this is finite set. Okay. So this completes our proof. Let's go back to blue. Here we are. Okay. Okay. Okay, so what we have seen now is, it doesn't matter if we have a replicable or not replicable claim xi, we always have the representation of the set of arbitrage-free prices in terms of the expectation under martingale measures. And now, I mean, this was actually why we started caring about this set of martingale measures, set of arbitrage-free prices, because there might be claims which are not replicable. Because if it's replicable, we're done already. So this is the purpose of the next proposition, is to understand better what happens if the claims, if the claim is not replicable. So again, fix our setting. Is a finite arbitrage free market. Okay. And now, if the claim, as usual, psi is not replicable, then, well, first of all, it's truly a set, right? This is what I somehow claimed already. So the infimum of arbitrage-free prices is strictly less than the supremum of arbitrage-free prices. So you see, this is really a difference. And even, can say even more, we know that the set of arbitrage-free prices is given by the open interval. So this infimum is really an infimum, and the supremum. So it's open to both sides. Here we are. So if this is don't forget this. If it's not replicable, so there exists no replicating strategy for this claim, then the price is really not unique, and it's given by an open interval. So this infimum, the pi inf and the pi sub, they lead to arbitrage. So they're not arbitrage-free prices anymore. Okay, that's a bit more work, but it seems doable for today. Right, that's. Okay. 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 So we start with showing that the price, the set of arbitrary prices is given by an open interval. And we have an open interval. I mean, basically, we want to construct for every price for every arbitrage-free price an element which is bigger and which is smaller. So strictly bigger and strictly smaller. Then we have an open interval, and in particular, we know that the infimum and the supremum are unequal. Okay. Okay, first, recall, this is the last proposition. The set of arbitrage-free prices is equal to the set, let's call it now I, to save some writing, which was the set of all expectation under some martingale measures of the discounted claim. Right. This is what we have already shown. And now we want to show that the set I is, I mean, it doesn't matter if, I mean, this is the same, I is the same than the set of arbitrary prices. So it's enough to show that the set I here is an open interval given by these two prices. Right. Step one. First thing to show I is a bounded interval. Okay, let's start with this. So if you have, I mean, I is a set on the real line. We have a set on the real line somehow. In order to verify that's indeed an interval, we just need to show that it's a convex set. And then if you have 2 points, everything in between is also in the set, and this is an interval. So let me pick 2 elements, pi1 and pi2, in this set I. This means there exist two equivalent martingale measures, Q1 and Q2, such that, well, this is the definition of this set I. Pi1 is given by the expected value of the discounted claim under Q1, and pi2 is the expected value of the discounted claim under Q2. Okay. And now, well, as I said, we want to show that it's a convex set to verify that's an interval. So let's take a lambda between 1 and 0. We have, well, let's define a new measure, Q lambda. Q lambda. Right, so Q lambda is given by the measure Q1 lambda times Q1 plus 1 minus lambda Q2. And this new measure, right, this is an equivalent measure, and it keeps the martingale property. Because, I mean, because Q1 and Q2 are equivalent measures, and they are both martingale measures. So the linearity here of all the operation, ensure that this is again a martingale measure. And this means if we look at lambda times pi1 minus lambda times minus plus minus 1 lambda times p2, this can be represented as our discounted expectation under Q2 and Q1, right? So this is just the definition of the set, and well, this is my definition, the expected value under Q lambda, of psi 2, right? And this means this is again by construction in the set I. Right. In other words, the set I as a set on the real line is a convex set, and such an interval. Okay. That's how it is. And now, well, interval, I mean, we want to have something bounded here. So actually we have a bounded interval. If we go back to the orange part here, we actually have seen that right. So this is, we note here again. So that's actually bounded from below by 0 and bounded from above by the supremum of the discounted claim of all omegas, but omega is a finite set. So this is actually a bounded interval. So as before, and is bounded since omega is finite. Okay, so we have a bounded interval. Was the easy step. Now we go to the hard step. The hard step is to verify that it is open interval. So this is what we show next. We need to show that I is open. Okay, so how do we do this? Well, we want to pick an element, so G for every, so we pick a pi, so arbitrage-free price in this set I. We want to construct two arbitrage-free prizes. Arbitrage-free prizes. Let's call them pi minus and pi plus, such that what pi minus is strictly less than pi and strictly pi is strictly less than pi plus. Wait, all right. So this means if we have an element in I, we can always find some element to the right and to the left. Okay. how do we do this? And we want to, so how do we construct them? Is we want to construct a new martingale measure, or actually two new martingale measures, which represent these two prices, P minus and P plus. So since pi is in I, there exists a Q in the set of equivalent martingale measures such that pi is equal to the expected value under Q of the discounted claim. So we need to construct, let's call them Q minus and Q plus in the set of martingale measures such that the expected value of the discounted claim under Q minus is strictly less than pi, and right, this is Q, and this is strictly less than the expected value under Q plus of the discounted price process, the discounted value of the option side. Okay. Okay, so we want to construct this Q1 and Q2. And the first thing is, okay, let's consider, we have this Q, the associated price process. So let us define the following martingale. MT by, well, M at time T is just given by the conditional expectation under Q of the discounted claim. Right. Right. And at some point, of course, we want to use that our claim is not replicable, right? Because you have only a chance to show that it's an open interval if the claim is not replicable. Okay. So that's the moment where we want to use it. So psi is not replicable. This means there exists time t, not in, okay, it should not be 0, so between 1 and t, such that it's delta mt, right? And this is, to recall it for you, by definition, mt minus 1. So this is just how we define it, is not an element in the set, let's call it K, which is the set of, or we take a position in the market, and we consider here the discounted price process. So this is our position in the risk key assets. So it's a RD valued and FT minus 1 measurable random variable. Okay. Because I mean, would there no such T, then this would mean, well, we immediately have a replicating strategy. So there has to be one time step in which we, or at least one time step in which we cannot replicate the movements of this martingale. Okay. And well, as for the first fundamental theorem, asset pricing, well, the nice way to construct martingale measures is to use this separation theorem in RM. So we use the same idea here. So we identify, since we are on a finite probability space, we can identify the FT measurable random variables with vectors in RM. Define right, no, T measurable random variables, X with vectors in R, right? Where, as before, I mean, we identify them by evaluating our random variable at these omega 1 to omega n. So these are the elements in our sample space. Okay. Okay. So what we realize here, that the set KT, the one we defined here, which are the discounted gains we can make in the teeth trading period, is again non-empty, empty, convex, and closed set. Okay. And what we also know is that the element delta MT is not in KT. Yep. This means by the separation theorem, there exists a vector that's called Z hat, and well, there exists also constant gamma in R such that okay, so this is Z hat just represents my linear mapping. So if I apply this linear mapping Z hat to elements in K, I am less than omega. So for all y in KT, this is less than gamma, and this linear mapping strictly separates this set KT from the element delta MT, right? So this is strictly bigger than gamma. Okay, so this is just applying the separation theorem. And now I want to remark two things. The first, that so the vector Z hat, right, which is an element in Rm, can again be identified with a random variable which is FT measurable. This is actually crucially a measurable variable that hat. The reason why we can do this is because we only, I mean, consider here ft random variables. So the number of values the vector can attach is determined by the ft measurability. Okay, so this is okay. And by the same rescaling argument, so we can choose our gamma to be 0. By the same scaling argument as in, so this was the construction for the first fundamental theorem, asset pricing, where we said, well, if this gamma is strictly bigger than 0, we basically can scale up everything and then it has to be infinity. So this is as in the proof of lemma. This was just for your reference, 3.23. Okay. Okay, so, and now as in the first fundamental theorem, asset pricing, I want to construct, I use this Z tilde to construct these two martingale measures, Q1 and Q2. So how do we do this? First thing is we want to ensure that the Z is, I mean, that head is not too big, so we do a small rescaling argument. So we take our Z head divided by 4 times the absolute value of that head. So what is the gain from this? Well, the gain we have is that if we look at the absolute value of Z for every omega, this is less or equal, which is strictly less than 1/3. So we want to have equivalent measures, so we need to be careful not to hit 0. And this holds for all omega and omega. This means we can define now two, well, rather Nicodim densities, Z plus, which is 1 plus Z minus Q, the conditional expectation under Q of Z conditioned to T minus 1. And now we have also Z minus, which is 1 minus Z plus Q. So we just swap with the signs here. Okay. So these are our will be. So now the first thing, and this is why we did this little rescaling of Z head. What we see here is that plus and that minus are strictly positive. Because these two terms are less than 2/3. So we can really define equivalent measures. Two measures Q1, Q plus and Q minus on our measure space omega T by the random Nicodim densities as usual plus Q is given by Z plus and Q minus also is defined by Z minus. And I mean, since these measures are strictly positive, this guarantees us equivalent measure. Right. So what we need to ensure now is that these measures Q plus and Q minus do the job. Right. So what do we want to ensure? Let's go up again. to check what we want to have. So we want to have that Q minus, that's where are we? So that's our goal. Right, so we wanted to construct two measures which are equivalent martingale measures, which assign the option a strictly smaller price and a strictly bigger price. Okay, this is what we need to verify. So I constructed now two measures, but we need to make sure they do the job. So first thing first, because if this does not work, we can directly stop. So first thing, we want to check that the price assigned to the option psi is really strictly less or strictly bigger. And I'm doing here Q plus, and then you can do the same calculation for Q minus. So so let's show Q plus net. Q plus is right. Okay. Okay, let's do it. So let's consider the expected value of the discounted claim under Q plus. And this is psi, right? So we use the nucleon density Z plus. Now we plug in so we use the density to go over to the measure Q. So now we have everything under the measure Q. So here we have the expected value under Q of the discounted claim plus this. Let me scroll up so that you can see the definition. So this is the tilde Z minus right, that tilde. So this is the last term here. So we get this one. Okay, so this is just plugging in the definition of that plus. And now, well, the first thing is, well, this is the assumption, the definition of the property of pi. So the first term here just gives us pi. Okay, and now let us use the tower property to introduce here another conditional expectation. So recall that T is T measurable. All right, so this is the tower property. And here again, we use the tower property just with respect to ft minus 1. Okay, that's, sorry, here's Q missing. It doesn't fit. Let me rewrite this because it's too long. So this is plus ft z t minus 1. And now, wait, sorry. So I just condition again on ft minus 1, so I get this conditional expectation with respect to ft minus 1, and the second term is already ft minus 1 measurable, so I can pull it out. I have this one. Okay, and now I have here my definition of M actually. So this is just M. So I have the expectation under QMT minus that plus conditional expectation of Q minus T minus 1 given Z of ft minus 1, right? And now I put these terms together so that I have pi plus conditional expectation, the expectation under Q of delta. So I put these two together by, again, conditioning on yeah, I can pull this out so I can get rid of this conditional expectation, and I'm left with that. Right. And now the same calculation for Q minus leads to Q minus condition, right? The conditional the expectation of the discounted claim under Q minus is equal to pi minus Q minus Z, right? And this ensures, hence, we get that the Q minus of the discounted claim is less than Q. Right? Because let me write down, then explain it a bit. But all right, there's nothing too much to explain, right? So we need to just ensure that this is positive, but whereas our separation theorem, where we started with, there's our separation theorem, right? That's bigger than gamma, so that's strictly positive. And this ensures that this is here strictly positive. Yep, and this is strictly negative. All right. So now it remains to show that this is it remains to show that Q1, Q plus, and Q minus are in equivalent martingale measure. So we need to do two things again. We need to check that it's a equivalent probability measure, and we need to check it's a martingale measure. And unfortunately, I'm running out of time. So this is where we start next time. Okay? I mean, you can look already in the lecture notes to familiarize you with the proof, or if you are just curious, please have a look. And then we do it next time properly. All right. Thank you for listening or watching the video.